so I must be moving on. Welcome everybody to this panel on Internet Resilience. Why panel on Internet Resilience, you ask? I argue that it's a cross-cutting challenge. That like security spans, it goes beyond protocols and to touch into infrastructure and governance. And as a whole, our community, surprisingly, has not paid much attention to it. So, needless to say, the internet has become the backbone of modern society and is increasingly under threats. The threats span over the map, and I just drop a few of them there. In the last maybe 4 weeks or something like that, we saw the Red Sea cut 2 days ago. Apparently it was a shipping container. That was the cause for it, but there were speculations about this being an attempt. And before that was the Starlink global outage that came out from a consolidation of the control software layer. But the type of failures that we've seen all over the map, and we are going beyond the first order, so beyond simple cuts. There are issues such as the consolidation or that we talked about before, or the interdependencies and the jurisdictional exposure that we've seen coming up on the network all over the place. And a third order of threats, such as opaque routing and hidden leasing agreements that don't let you see even the scale of a failure, or forecast the scale of a failure. So today, we put a panel to bring up these questions that we like to ask and figure it out as a community, and in that way, steer the conversation toward this problem that we think is key for us to address at the moment. So, beginning with what do we know about internet risk and dependencies? How do we actually deal with them or influence them through technology or operations or government? And then, what is the demand from the research community and from practice to try to address the resilience issue? The panel has Adrian Berg that, I don't know if you all know, should know, and if you don't, there are 3 papers from his group, so you will learn a lot about what these guys are doing. But it's basically focused on the design of secure next-generation internet architecture. And Rich Pakir comes from ISOC. He's been working on this topic of consolidation and monitoring of failures and resilience at the internet scale for a long time. And Johanna Ulrich, who's been working at the intersection of CS and classical engineering, looking at specifically at the topic of the internet and the power grid. That the moment you start looking at internet resilience, it's become one of the key points. So without that, the way we're gonna go about it, we're gonna have a short position statement from each of the panel members. And then we're gonna focus the conversation on the questions that were up. Then we open the floor for everybody to ask questions. Adrian, you wanna start?
All right. Thanks so much, Fabian. So one aspect we've always looked at in our research is attacks, attackers that try to prevent availability for the most part, or also eavesdrop. And essentially, a big challenge in today's internet, and I'm sure all of us have read papers that start out saying, well, these protocols were not designed for an active adversary. And so the question is, how can we really design systems that are secure under active adversaries? So the big challenge we have in today's internet ecosystem is, again, most of these protocols were not designed for security, and oftentimes people say, well, we can add security later on. But as a result, we've had a number of attacks over the years, right? New ones continuously coming out. And a big issue is that we don't design the systems also with formal methods that allow us to prove certain properties about the systems. This is certainly starting. There's many efforts doing this. But for a critical infrastructure like the internet, it's surprising how little has been invested in doing formal methods analysis to find attacks and vulnerabilities before the systems are being deployed. So as a case in point, we published, and typically our research group is not doing too much in the ways of attacking systems, but every now and then we stumble across and do publish some papers. And we had a paper at the Usenix Security Symposium about 3 weeks ago. It's called BGP Vortex, and it's a new attack on the BGP routing, interdomain routing protocol. And oftentimes people do say BGP can have convergence issues, and BGP Vortex is exactly an attack that prevents the BGP system to converge. Essentially the way it works is it's probably most of the people here are familiar with BGP widgets, which create an instability that never stops, but we all know if Gao-Rexford rules are being followed, then these widgets should not be feasible or should not be possible. But now we found that by using BGP communities and a specific attribute, one can actually again inject a BGP update that creates oscillations, indefinite oscillations that keep on going. And what's serious here is that it's among entities that do not include the adversary. So essentially the adversary can inject messages, BGP updates that create these permanent oscillations. And so the point is, if we had ways to formally analyze BGP and show and study the convergence process, hopefully we would not have these kinds of vulnerabilities. So with this, over the last actually 16 years, we've been working on the SION architecture with specifically security in mind, designing the whole system essentially for a secure internet that also enables formal verification. And the team of David Basin at ETH has been doing a lot of work in this space to prove the properties, and they found vulnerabilities in SION based on the design. Even though the whole design was specifically made for security, still mistakes were being made, and we've made errors, and we hope all of them have been found. And so this creates a much safer internet. So with respect to convergence, also the way SION operates is without a convergence process. So paths are being created, but there is no global convergence to figure out the one path that's going to be used, but simply paths are created and they can be used right away. And so there's, in the absence of such a convergence process, one can now prove formally very strong properties about the stability of the system. And this shows that if we take security into account and we attempt to also work with formal verification from the beginning, the design of the system can actually end up quite differently, excluding fundamental vulnerabilities such as this BGP vortex through the design of the system. Right? So I don't know how I'm doing on time, or maybe it should be enough.
You have more to say?
Should I proceed?
Johan? Yeah.
Okay. Yeah, and my colleague was just speaking about the internet. Now we have the situation that the critical infrastructures are dependent on each other. So the internet relies on the power grid. The one thing is obvious. I mean, every router, everything needs somehow electricity. But on the other side, nowadays, we even need a functioning internet to operate the power grid successfully. The one thing is that, the one reason is that we have digitalized the power grid, but even beyond that, we have a connection and a dependency between the two, because you, and we all have more and more devices that are on the one hand connected with the internet, and on the other hand need electricity. And the biggest challenge for the power grid is a large changes in consumptions as they destabilize the power grid and eventually cause blackouts. And one way to do this is, or one thing when this happens is if we all watch a major football match and there is the break, we all go either to the kitchen or to the bathroom, and this increases the power consumption all of a sudden. The good thing is we know when there is a match. But if you assume an adversary that creates a botnet and of all the devices you have at home, the IoT devices, and we know the S in IoT stands for security, so the adversary can also suddenly increase consumption. And even in absence of such malicious intent, it's possible because we operate a lot of infrastructure, hardware and software, that is monoculture. So many things operate the same technology. And if that fails, we know software failures are all around, we have another problem. We have experienced that with Ethereum in the past, that all stopped mining because of an error, a software error, and it decreased consumption. And there was also a long time ago a leap-second error in Linux distribution that increased consumption. So that's the problem with the power grid and the internet in combination. And a fundamental flaw is how we actually engineer the systems. Or let's say it's not a flaw, it's how it works, because usually if we create a new system, we think of it as an add-on. If I think back, my great-grandfather, he bought a new engine to woodwork, because that was his job, and in the evening he provided electricity to the neighbors. Back then, if this engine failed for 2, 3 days, weeks, nobody cared, because the neighbors would just replace their 1 or 2 light bulbs again with a candle, as they used before. Nowadays, 2 weeks without electricity, I mean, you can ask around for the locals. They had a 1-day power outage here in Portugal and Spain in April. You can ask for their experience. I guess it was not that much fun. We have the same situation with an elevator. At the beginning, it was an add-on. If you live beyond the 10th floor, no. And it's the same for the internet. If you're older than, let's say, 30, the internet of youth was an add-on, which it is not now. So what I want to conclude is actually the people who create the system and the time when the system is created is somehow graved into the system. There are some assumptions and worldviews, and they are implicitly there. And this is why we shouldn't only see the technological things. Actually, our colleagues from STS, so Social and Technology Studies, they call this a socio-technical system. So they put us within the system borders and say, well, this, we also have to consider you. And if you take then the system to either another time, another use case, or just another environment, it might fail because one of these assumptions might be broken. The problem regarding resilience is how can we reveal these assumptions? Yeah.
Hi everyone, so thank you for the invitation to the panel. So yeah, resilience I would say for the Internet Society is quite a big topic. First of all, the Internet Society stands for a globally connected, secure and trustworthy internet. So all those 3 words is very aligned to a resilient internet. But the resiliency is a quite abstract construct, right? So resiliency might mean different things for different stakeholder groups. So, but the Internet Society basically look at resilience from a more global perspective. So we had to build resilience on a few pillars, and things that we are looking at is infrastructure, performance, security, and market readiness. So a resilient internet is not only something which is technically robust in terms of infrastructure or security, but we also strongly believe at the Internet Society that a resilient internet should also provide affordable connectivity and also what we call meaningful connectivity to people. As you know, internet access is not equal everywhere in the world. So one of our foremost missions is actually to improve internet access around the world and also improve the internet resilience wherever it is. I always have that example when there were cable cut off the coast of Ivory Coast, and I was in South Africa in a bank, and the phone system was stopped working during that outage. And you see the level of dependency on a few systems, which makes the internet quite fragile. Understanding also concentration and consolidation trends on the internet is also important, and these are important factors that you need to factor in your overall resilience equation. We also have a big focus on internet exchange points, where it is important for traffic to stay local as much as possible, because this is also allowing people or networks to reduce their dependency on expensive transit links or international links going through submarine cables. And we have also seen that not all countries have the same access to whether it is internet exchange points or access to high quality access through submarine cables. We have examples of countries, landlocked countries in different regions of the world, where they depend heavily on their neighboring country. And this comes with a lot of considerations with regard to resilience. So usually you have a single point of failure, and when things goes bad, whether it is a power outage or a network outage, countries which normally are sovereign and independent are also impacted. Coming back to the Portugal and Spain outage, there was issues and on the internet in Morocco, for example. So it shows how Morocco is highly dependent still on other countries with regards to their internet, even if there were no power outage in those regions. Again, what I want to say is that resilience is a broad concept, and every player needs to play their role of resilience at every layer of their stack and in every system that they're building. And it should be a part of the design of any system that we are building.
Something that I've been wandering around, I mean, like for a while, listening to what you were saying and something that's happening to some of the work that we have done, I wondered to what extent then a work on internet resilience require a change in the way that we do research or that we review the research. Like it seems to be, there's a different type of analysis you need to do for this kind of analysis, this kind of work. So you're not going to run it in a data center. You're not going to run it with a lot of users. You're going to have simulation-based analysis on some of the work because you cannot play around with the power system, or you're going to have a very heterogeneous set of data coming from different countries around the world that you cannot easily compare or merge in any kind of nice, correlation graphs. So how, in your opinion, the type of work that we should be doing on internet resilience changes how we do research and how we evaluate the research?
Right. So, yeah, it's inherently very challenging to perform analysis of today's internet, because not only because you cannot simply have a digital twin with all the routers, but also with all the policy definitions in all those routers. The router softwares can be inconsistent, or different routers on different softwares, and this can cause effects on how quickly the system can react based on how different parameters are being set. But to make some progress, an approach was, and there's a paper coming out at the SRDS called Domino, to create a test bench where you can then do these kind of experiments with BGP and run on some topology to also see the impact of different configurations or different parameter settings. But we need a lot more in this space, right, to test our today's internet based on very large scale outages. That's an area that needs a lot more work.
Yeah, so actually, the internet is still in a very good position, actually, that you can, to a certain extent, try it, or at least have test setups. That is, for example, what you don't have in the context of the power grid or these dependency aspects. Usually I have a slide with me showcasing the model that we used in our very first paper to model the whole European grid, and you don't have to be an expert to see that this is very coarse-grained with a few boxes, because there's not a more precise model of that. And despite the fact that such models are available, they are not available to us as researchers. So there is basically the questions whether we gain resilience by publishing the model, or do we gain more resilience by hiding the model. So that's at least by the power operators, the alleged reason for not providing the model is security and resilience. However, I doubt that this is working, because we know where the infrastructure is. And for somebody who wants to attack it, for sure they will find out.
Yeah, if I may add, I think research projects produced by the academia, like Planet Lab and others, I was talking to Serge about their project on SLICE, are extremely important for researchers to be able to test concepts and around resilience, right? But I think the biggest issue is having reliable data, and also data that is not about just simulated data where you're testing a model, but also data which is representative of the real world. And we know big players are usually very cautious about sharing data to researchers, so unless you have very good relationships, but it is very difficult to have access to data about the different nodes of CDNs or other big network operators. So if this data can be provided to researchers, we can test resilience concepts and models on actually real-world data. I think that could be useful.
Because of the time, I think it's better we open the floor if anybody has any question.
Well, the first question was, what do we know about internet risk and dependencies, right? So you scratch the last 3 words, right? What do we know about the internet? I know SIGCOMM' and IMC spend a lot of time measuring the internet, but it becomes kind of more and more private. There is less information available about it. With multiple stakeholders, we don't really know what's going to happen when something occurs. All right, so I think that's part of the issue. Another one is what we didn't talk about, the economic aspect, because if you want to be resilient, you have to have a backup plan, right? Whether it's a candle or analog radio, which work here in Spain and Portugal during this great blackout. So somebody has to pay for it, right? So these entities have to plan for this extra infrastructure. So I think that was kind of discussed, right? Because resilience doesn't come for free. It's not only have to be planned for, but it has to be paid for. So I'm just wondering whether you can comment on this kind of economic aspect of resilience. You know, who is going to pay for it, what are the incentives, and what's the best way to do it in practice?
Yeah, so resilience is very important. There is actually a lot of resilience in today's internet. We just cannot use it. I heard at some internet exchanges, in fact, there are 3 parallel systems running, but only one is being used and the other 2 are failovers. And if we use systems where you can actually use all 3 at the same time, then you have a much more dynamic process. You can make use of more resources. Plus, in some cases, the failover is not working, and then you have these redundant mechanisms, but because they're not being used when they should be used, the failover mechanism is not triggering. And so here the suggestion is to use multipath, for instance, more aggressively, right? The internet has huge number of potential paths, but BGP cannot make use of them. And so we've seen, so Cyan is, the Cyan architecture is naturally a multipath approach, and there we see huge resilience gains because all these paths are active simultaneously and the system can switch very rapidly between them or even use all of them at the same time. So you're not running active-passive anymore, but active-active. And so you ask specifically, well, who will pay for the redundancy? And so the answer will be that one possible perspective is, well, there is a lot of redundancy already, we just cannot use them based on today's systems. And so we should think about how can we unlock all this huge number of diverse paths and so on. So it's been interesting, for instance, the outage in South Africa that you mentioned with the undersea cable cut. There probably was another path, but BGP just takes a long time to detect it. It takes, on average, 3 to 5 minutes for BGP to, on an actual intradomain failure that wasn't anticipated, to switch over, right? Even the timers are typically set to 90 seconds to not do anything until the system is really disconnected for 90 seconds. So using systems that really switch much faster, I think can add a lot of resilience. So without spending too much, that would be one direction.
Okay, so I'm going a bit on the meta level on who should pay it. There's on one hand the balance between, obviously we can say it's like an insurance. Getting an insurance isn't a very sexy thing you want to do, and nevertheless you usually have an insurance just in case you need it. That's the one aspect. And the other aspect is that our society, and I mean we're here on a scientific conference, we're the extreme in our society doing that, is preferring novelty over continuity. And resilience is a matter of, for technical infrastructure, a matter of engineers being there for maintenance. And if you maintain a system properly, you have usually better resilience. And if we somehow make it that these engineers are seen more, obviously novelty is also interesting, but we have also to bring their work to the forefront, because that is actually what our daily life is based on. So if you have a properly maintained infrastructure with properly educated staff that has experience, it's usually better.
Yeah, I think that's an important consideration, the economic aspect of resilience. Obviously, someone needs to pay the bill, and it costs money. But maybe we can reverse the question and saying what could be the cost of insecurity, right? If a network goes down because of a lack of resilience, this might cost even much more than having a redundant link, for example. So I think that aspect should also come into the picture when people are considering whether we need to invest into resilience. Another thing that I wanted to talk about, the economic aspect as well, maybe looking more at the macroeconomic side of things, is that obviously resources are limited and funding is limited as well. And obviously what we are seeing now is that more funding is going towards new emerging technologies like AI and things like that. So I don't know the answer, but if the flow of money is going towards one direction, it means that there is potentially no flow going to in consolidating existing infrastructure, making it better, and making sure it is openly accessible, resilient, and robust. So these are, I guess, considerations that policymakers should have in mind when actually dealing with investment into technology and infrastructure.
Actually, it also resembles the same question that we have, let's say, on the European level at the moment. On the one hand, we have an economic crisis, at least in certain richer countries, so we should, on the one hand, focus on novelty and novel products there. On the other hand, we have a threat from outside and have to make ourselves resilient, and in the end, we cannot say one or the other, but we have to make to both, no matter how, but we have to do it. Yeah.
Hi, Chris Misa, University of Oregon. I just want to follow up on this question of the internet as a technological system where there are, of course, emergent technologies, and pose the question to the panel, do you think that there are opportunities to leverage emergent technologies? I won't say AI, but for example, optical topology programming or satellite networking, to leverage these kinds of things to improve that trade-off between cost and resiliency?
Somebody on the here on the floor said it's a killer question, because mostly I think we cannot say it.
Well, AI, also introduces many vulnerabilities on one hand, but on the other hand, it can definitely help maybe react faster and make smarter decisions. But fundamentally, looking at it, we don't still understand how to make AI safe in a way or many people are working on this, how to make the outputs predictable. And so introducing such a system for reliability can be a double-edged sword, right? You introduce yet another system that an adversary could perhaps exploit to create even more unavailability. So it's a big challenge. Although on the other hand, AI techniques are used to make systems also more secure, to find vulnerabilities, or also to tune systems in an adversarial way, in an improved fashion to make them more secure. So there's a lot of facets to this problem, certainly.
I think I will go into the same direction. We have, on the one hand, it might be usable to create support systems. On the other hand, we lose with automation management capabilities for emergency routines. So there's the story, and I think this makes it visible for everybody. The more pilots go with autopilot, the less they are trained to handle emergency cases. The question is, but you have less skills. You need, as a pilot, less skills on the day-to-day business. So maybe we see the same trade-off there, but I don't know yet.
I think with the introduction of AI, we are just shifting the issue of resilience to, I would say, another paradigm, the paradigm of AI. So just as we are talking about infrastructure resilience, we should probably in the future, maybe on next year's panel, it would be the resilience of AI systems. Because we also need guardrails for those systems. Because as you know, it's garbage in and garbage out. So how do you know those AI systems are not biased? How do we know they are treating things in a fair fashion? So the concept of resilience, which is about making things secure and robust and reproducible and things like that, would also apply to the new AI paradigm that's coming up.
And this thing needs a lot of energy, and then we come back to the more energy. So it has thousands of consequences that we might not be aware of.
Final point. So I do believe that formal verification is is a key to making our world more resilient and more safe, more predictable. And their AI has a promise to actually support writing proofs. So in this case, AI, if it cannot do it, then, or if it makes a mistake, then the proof simply doesn't go through. But I see a lot of opportunities in connecting AI in that sense to assist creating the formal methods and the proof systems, the proofs to proof systems secure. So that's, I think, a very nice opportunity for researchers.
So I want to go back to power grid and internet in the sense that, so the power grid people are in this process of revamping the power grid, going from a more or less centralized architecture to a fully decentralized architecture. And that looks like it opens up enormous opportunities for co-design between internet architecture and power grid architecture, but it also opens up, very scary opportunities for new vulnerabilities. And I sort of was wondering whether, there has been any sort of work in this area that sort of demonstrates what can go wrong, or how could we benefit from this, getting this co-design right?
I mean, what both infrastructure share somehow is their story, insofar that they start decentralized, become more centralized, and maybe become more decentralized again. From co-design, that's not that easy. What I think could be learned about strategies, how to handle certain things or attitudes. I think computer science is generally better in reacting to situations, to be faster in reaction, while the energy sector has a tendency to consider what they are doing more in advance or before bringing the product out, because there is more energy involved. But apart from that, so far there is not much overlap between the two sectors, and it could be worth to go in that direction. I hope that handles your question to a certain extent. No?
Yeah, one of the questions that I keep coming around is the issue of the interdependency that we have built. So the focus of consolidation, or the interest in consolidation, is coming not just because of the consolidation at the service level, but really for the interdependency that somebody pointed out is typically hidden. So that if your BGP fails and suddenly the service that you're depending on perhaps is completely out, and then you have, like you don't see updates on your Slack, although everybody in your Slack group seems to be there. So there is this very tight interdependency built into the stacks of the software that we have built. And I really have no idea how to go about tackling that problem as a researcher. Like, how do you go about proving the resilience on these very opaque interdependency stacks?
Right, it's surprising how many interdependencies there are that we know about, and it seems industry is not doing too much about it. For instance, between RPKI and DNS and BGP, all relying on each other in a circular manner, that is a big issue. And so in the IETF, we should, on standardization, we should be aware of these interdependencies and really try and ensure to remove one of these cycles after another, if possible. And I was surprised that people don't seem to care all that much when these interdependencies are being pointed out. Because when we see large-scale failures, oftentimes you see that one of these interdependencies loops occurs, that is not one of these dependencies is not satisfied anymore, then the whole cycle breaks down. I mean, one example also was at the Facebook outage at the time, when the door locks were dependent on the internet and so on, right? There are so people couldn't get into the data center anymore to fix some of the issues. So unfortunately, some of these dependency loops are then powerfully demonstrated with real-world outages, but many of them, people who look into this, we see they exist, and then people don't seem to care all that much to do something about them. So I think the urgency is not quite there to fix these kind of issues, it seems like.
Yeah, I was wondering, like the Facebook case, I thought it was I love that example. The doors being, you can open the doors to go and fix the problem that is leaving you the door locked. How much of the problem is coming because of companies are not required or incentivized to actually do any of this analysis on resilience? And the incentive is actually to hide the fact that you have a problem. It's likely going to go against your share value, so just swap it under the rug or something like that.
Firstly, I just wanted to jump back on the ITF that you mentioned about that. I think it might be a good idea that, because we have like security consideration in a draft, maybe we should have the resilience consideration as well when people are building standards. So I think that could be one. With regards to your question, the same thing. I think, again, when designing system, they should have that resilience mindset from the onset, right? And make sure that any system that they're building, especially it is consumer products where now a lot of businesses, a lot of people, and in some cases even emergency services are reliant to those. Yeah, so that aspect of resilience needs to be taken into account.
One aspect that we also see that's a problem is that we are highly specialized meanwhile. So we have even within computer science, we don't know everything. And there are the expert for A and the expert for B's. And so usually it helps, or it might help that you understand the principles that the other discipline or subfield is working on. So just to highlight some very easy and maybe funny aspects on jargon. So in computer science, we say if we have a 1 and a 0, and after one it's a 0 and a 1, we flip the bits. And electrical engineers, there are some around who said, well, this is a phase shift by 180 degrees. And I thought, well, yes, but Also the question, for example, what's fast? The one would say, 30 seconds, that's fast, because for a power grid, it's fast. For IT, it's more, yeah? So I guess also to work more interdisciplinary is one thing, and also with regard to the assumption, it could be helpful to do studies like in sociology to ask people in interviews. The problem is that we have to go as engineers with them because they know the methodologies and we know what to ask for, because you cannot send a sociologist there and ask random questions about BGP. That doesn't work.
There is an interesting aspect in this space, which one time I went around ITF and asked the BGP graybeards, how long would it take to reboot the internet? Oh. So interestingly, the answers are quite consistent. There are only 3 different answers people would give. And some people said 24 hours, others said 48 hours, and a few said never. So this is also to the point about circular dependencies and these aspects, that it really is believed that, and of course it doesn't make sense to ask the question because we're not rebooting the internet, but we have seen large-scale events, and so the question does make sense in the context when you have large-scale outages, that if you design the internet to make it rebootable, and if you remove these circular dependencies, that then actually the system would become a lot more resilient and be able to reboot much faster. Hopefully within, I think even a second is long. Things should, well, not for rebooting perhaps, but a lot of these outages should be fixed below fractions of a second for the kind of purposes we're using the internet for.
Any other question?
From our internet measurement community point of view, do you think our industry or research community have sufficient effort in collecting internet measurement data to capture the resilient problem? In your opinion, if not, what we should do to capture more data?
Right. Definitely more data will be very useful, especially for these large-scale outages. There are very good repository. CADA is, of course, doing a lot of work there, and that is extremely useful, and of course, more is better.
Yeah, I would agree on that. Definitely more data would be useful, especially that, as you know, internet measurement systems are not equally deployed in all places and all locations of the world. You would have gaps and black holes, basically, where you don't know really what's happening because we have a lack of visibility, we have a lack of probes in those different places. And usually we are using this biased data to build models and now training models and everything, and it might not be the reality out there. And therefore, if we are basing ourselves on those, I would say, biased data, the output would be great. So definitely, it demands collaboration between different actors, whether it is the network operators themselves, regulators, and perhaps researchers as well, like have a more coordinated effort about internet measurements and the placement of probes, and also putting data which is not openly accessible, but at least accessible to some extent to researchers for us to be able to do our work.
I wanted to comment on one of the statements that was made earlier on about the awareness of the fact that reliability needs to be addressed. I think this is partially due to the fact that the costs for addressing the reliability needs to be borne by providers like Facebook, for example, but the costs in case of a resilience issue needs to be borne by the end user. And so perhaps we need regulators, similar like in the airline industry where there is disruptions, you get compensated as a customer, that in case there is an outage like Facebook, or I mean, I don't want to blame only Facebook, but any outage out there, that users that are facing it get right for a compensation.
By the way, the compensation for the airlines only in Europe. I come from the US and it's on you. So.
The problem with compensation is that it works quite well as long as the outages are, let's say, medium-sized. If you really have a super significant outages, no matter of which infrastructure, the company behind just goes bankrupt. And I think this is for this medium-sized, this works well, but there, it's already there. So usually a company, when contracting a data center, they have some penalties there if the availability is not met. But the question is, what happens if the damage is so high that the economic loss returns us back to 10 years or 20 years. And this sounds maybe overestimating, but for the power grid, there is a report of the German Bundestag, of their scientific organization, and they say if 10 days of blackout brings us back to the situation after the war, and I guess a large-scale outage of the internet wouldn't bring us back to a war, but for sure 1 decade at least, if not 2. Yeah, there are assumptions, but still, I think the impact is much higher than we can imagine.
Any more questions? I want to thank you guys again. That was great. It's a great conversation, and thanks to the audience as well.